Perfect. So, what changed with LLMs? AI inference has been done at large scale in commercial systems for more than a decade now, since at least 2010 or so. Why is it suddenly a problem, and why hasn't it been in the past? So, you know how AI was first invoked in the 90s or so, but it wasn't actually used because we didn't have the hardware for it. We are reaching a similar problem again, but in terms of large scale inference, where it can't be used to its full potential thanks to terrible hardware out there today. Well, it's not really terrible, but AI is just a whole new scale we have. So the reasons can be put down to three main big reasons. One is unprecedented model sizes. The second is large memory footprints, even in proportion. So you would think that, okay, you have a large footprint because it's a large model, but even in proportion, this is quadratic as opposed to linear or so for most other neural networks. And third one is the low potential for parallelization when it comes to LLMs. Uh, so
Why is there a quadratic growth rate compared to linear?
because the attention mechanism is by design quadratic in terms of both memory and time.
Right.
And there's more to it, which I will explain in a couple slides. The first one is unprecedented model sizes. So a 70 billion parameter LLM like Llama 2 today is about 140 gigabytes, and this is just for storage. This is not for actual inference. So I put the calculation up there, 70 billion times 2 bytes, which is FP16. So yeah, 140 billion bytes. And below that, you can see the data sheet for NVIDIA H100, which is the state-of-the-art GPU we have out today. And the best one has only 80 gigs of DRAM. So you cannot fit a whole model, just storage on a whole GPU, on a whole state-of-the-art GPU, which is how the state of things is today. And the large memory footprint, as to what Arif asked about, first, we have the KV cache problem. So for those who are not aware, KV cache is a mechanism used to make inference in LLMs faster. So the decoder for a transformer is causal. So the attention of a token depends on its preceding tokens by design. So at each generation step, we are recalculating each previous token's attention, and this is obviously not optimal. So you can save it by, what's that one? Dynamic programming, where you store things. Yeah, this is sort of a dynamic programming approach where you cache the previous keys and values on your GPU instance, so you don't have to recalculate it every single time. And this is called a key value cache, but the key value cache is even bigger than the model itself. And the worst part is you need one for each instance being used today. I will explain it soon. So take for example the Anthropic 52 billion parameter model. The KV cache for that is 2, which is 2 times, which is 1 for key, 1 for value, times the dimensionality of the model, times the number of layers, times the size, which is FP16 here, times the batch size. Say, for example, you're hosting this model and you have 512 users. You need this number times 512 to store the KV cache for all the users. So that comes out to 17 gigabytes times 512, which is 9 terabytes, which is just not doable.
So I'm not following why the thing increases with batch size because the weights are the same, right?
Oh, this is Sagar and I had a massive argument about this actually, because batch size here means a different thing from the thing you're usually used to. This is not the training batch size. This is inference batch size, as in how many people are inferring from the model at the same time.
Okay.
Yeah.
So, but if you're storing the value from the cache, why would you have to multiply the cache multiple times?
Because
Or
each person has a separate instance where they're generating completely separate texts. So the KV cache for one person does not apply to the other person. They have their own KV cache. Like, for example, you are summarizing some textbook you need,
right.
and I am asking for a poem. My KV cache is for the poem, which is not applicable to you. So you have your own KV cache. Each user has his own KV cache.
Okay. So, all right. The one thing I still don't follow.
Mhm.
So we have the key value weights, and the cache is the output of the of
The previous tokens.
the output of the previous token. Say.
Mhm.
Oh, okay, okay. So everyone has to
Everyone has
stay
their own
to.
sequence, right? Yeah. So it adds up, and the more users you have, the more it just scales linearly, which is not doable. It's not sustainable. So that's 17 gigs just for one person if you don't use any optimizations. And like I mentioned before, the attention mechanism has quadratic time and memory complexity. It scales with the input sequence length, so it blows up really fast. And the third point is the low potential for parallelization. So the autoregressive generation of tokens is sequential in nature, which means that each token prediction depends on previously generated tokens in text. So it's really hard to parallelize it when it is sequential by nature. You can only go one by one. So this impacts the scalability of LLMs to a large extent. And these are the three big problems. Now we can go into some optimization strategies. Does anybody have any questions about the problems? Okay, perfect. Oh, and I should have said before, this presentation closely follows a really good blog post by Lillian Weng. I will link the blog post in the channel so everybody can read. And it will probably explain all of this much better than I am. Mm, so the optimization strategies can be divided roughly into five main categories. So the structure of this presentation is going to go as follows. I am instead of deeply diving into one paper and thoroughly conveying the entire thing, I'm gonna follow the approach of a survey paper where I will discuss state-of-the-art strategies used currently just vaguely so everybody has an idea of what is out there because I believe that when it comes to things like this, a BFS strategy is better because you'd rather know of many things than know some things. So I'm probably not going to have the time or the slides to go into any of the papers today, but I will refer to them and maybe in a follow-up presentation, I can start going into the best ones one by one a little bit. So some of the main strategies we can use is to one, increase parallelization to scale across multiple accelerators. Um, this is hard both from a hardware and a software perspective. Software because parallelization is hard, and hardware because it's hard to distribute one model between different AI systems, both in terms of the model and next because it severely affects the bandwidth you can have because the bandwidth within silicon is an order of magnitude faster than the bandwidth between chips using cabling. The second one is memory offloading to manage memory utilization at the cost of latency. So this is called the spill and fill approach, where you spill out weights and activations you don't need at the moment and then pull them back in when you do. Obviously, this adds the cost of latency the cost of spilling it and filling it back in, but you save a lot on memory. But this is okay because today the biggest bottleneck is memory and not speed at all when it comes to most big models. And the third one is smart batching strategies. Not much to say there.
For the second one,
Mhm.
when we say spill, we're basically moving it to like swap.
From SRAM to DRAM. Sure, sorry, I should have specified.
Okay.
Sorry, stupid question. What is SRAM? What is DRAM? What's like actually different between the two?
So within computer architecture, you have hierarchical memory, you have L1, L2, L3, and then storage. So each L1, L2, L3 gets slower as you progress. So L1 is really fast, L2 really fast and really expensive, L2 less fast, less expensive, L3 cheap. L3 is the RAM on your computer. Mhm. So SRAM is right next to your CPU. So ideally, you would want to keep everything in SRAM so you can immediately access the weights and the activations. But obviously, SRAM, you don't have much of it. I think the new NVIDIA H100 only has about 8 gigs of, not even 8 gigs, I'm tripping. Like 2 gigs of SRAM, which is barely enough, but it has 80 gigs of DRAM. No, 2 gigs of L2 and 80 gigs of L3. And then when you go to DRAM, it has a lot more out there because DRAM is just cheap. Like
What
everybody
is
has DRAM.
DRAM stand for? And I know VRAM is what I'm familiar with. How does
Mhm.
it relate to DRAM and SRAM?
DRAM is a hardware description. SRAM is not a hardware description. So DRAM is a type of RAM. It's usually used to refer to just cheap RAM.
Okay.
And SRAM is I forgot what the S in SRAM stands for, but anything within your vicinity is referred to as SRAM. Like your caches are referred to as SRAMs too.
Do registers count as SRAM, or is that just?
No, the registers are one level ahead. Mhm.
Why expensive? Do you mean computationally expensive or?
Computationally expensive, yeah. Oh, no, no. This is just monetarily expensive.
Okay, that's.
SRAM is just expensive to buy, which is why you can't have a lot of it on a computer. Hmm.
With DNS are for dynamic and static. I guess that makes sense because
I
dynamic
see.
has to be randomly accessed.
Hmm.
Static would be figured access.
That makes sense.
Um, about the second one, right?
Mhm.
What's the actual guesstimate of like, when does this become a noticeable problem? If it's really true that your constraint is memory and, like the time won't be severely affected, what's the extreme of this that we can see be pushed? Do you know what I'm saying?
No, I'm sorry. Can you repeat that?
So I see it as that like, I don't understand how much benefit you would get from, expanding out the memory, right? Like, let's say that like on your hard drive, this is your CPU right in the center, and then you would just have like a circle pattern of memory, right? So
Mhm.
it's supposed to access at least radially. What's the upper limit of this where we start to see actual performance impact?
Performance impact in terms of time or memory?
Speed.
Speed. So this latency is not referring to, so if you have too much RAM, it's not going to affect your latency. It's just expensive. This latency is referring to the cost of spilling, as in when you don't need something from your model port, you spill it to the DRAM. So having to access it again from your DRAM and then pull it back in, that is an extra cost.
Okay, so someone mentioned swapping earlier. Is that the best analogy for it? I know swapping is usually with DRAM like your hard disk, but
Hmm.
that's the same sort of idea, right?
You can swap, yes, data.
And is this ever like brought up as an example here? I know that's extremely slow in comparison to Astra.
Like actual storage? No, never. You will never use it.
Okay.
Yeah.
Yeah.
Well, I guess that's where you always start from if you look at it that way. You always start from disk. Hmm. And the fourth one is the most common, and I'm sure most of you have heard of most of these strategies. These are actual neural network compression techniques like pruning, quantization, distillation, and so on. Pruning refers to removing unnecessary parts from your neural network. Quantization refers to compression by reducing the data types. For example, you train an FP32, but you can infer an FP8 because you don't need that much information for inference. And distillation refers to knowledge distillation, where you can train a smaller model using a bigger model. I will talk about those three in detail soon. And then we have architecture-specific optimizations. This means just completely new architectures which base off of the older ones and are much better at these are designed for efficiency as opposed to performance. Any questions about these?
Smart patching strategies. Can you give me an idea of what a smart patching strategy is versus stupid one?
I actually didn't get there in my presentation
Okay.
yet, so I can't.
Alright,
That's for next day.
cool.
We can start with knowledge distillation. Uh, so for those of you who aren't aware, this uses a student-teacher model, where a smaller or lightweight model, referred to as the student model, learns from an expensive pre-trained model, which we can refer to as the teacher model. So if you can look at the infographic there, you have a much larger teacher model, which knowledge transfers to the smaller model. We can discuss how this happens in the next slide. They are trained on the same data and infer on the same data, but you get benefits in terms of size, and speed, and the trade-off is performance. So this was first introduced in 2015 by the man Hinton himself, Geoffrey Hinton. Uh, so the student model mimics the teacher model by minimizing distillation loss. And I can explain the equation for distillation loss down there in book. Do we need a book? No, I think I can just do it here. So this is the loss for the entire knowledge distillation process, and it's combined, and yep, and this is just the loss for distillation, and you add to that a hyperparametrized cross entropy loss. So I'll explain how that works soon. So first, for the distillation loss, uh, you calculate the distillation loss between the softmax layer of the teacher model and the softmax layer of the student model. So ZS here stands for the largest layer right before the softmax layer, on which you traditionally use the softmax layer, but we have a small change here.
Sorry, how do you make sure that the dimensions of the softmax that are the same? Because like, let's say like, if I'm listening to this like, it's like more like the bigger language model had like a vocabulary size 32K small and model had size 16K. How do you compute softmax across that? Or is the vocabulary size the same across two language models?
You use the same data set, so I assume it should be the same, but I actually didn't look into it. But
No,
that's what I think.
That's exactly
Yeah.
correct, no? It's because it's the only thing you're reducing is the latent layers.
Yeah.
So the start first input and the output is exactly the same.
Okay, so you're actually looking at an actual data set vocabulary.
Yeah, it would
Okay,
be
oh,
the-
so it's in data set with,
it's the latent
Yeah,
layers
yeah,
that you are minimizing.
So T is the temperature here. We select a relatively high temperature. So the use of temperature here is that we want to soften the probability curve. So do we have a marker here by any chance?
I think gaps.
I think I have one in my
Oh, perfect.
thing.
If not, I can just use my notebook.
That's all good, I think.
Pointers.
Yeah, I have it.
Oh, perfect, thanks.
Oh, there's one on the ground.
There's one, right?
Over there on the ground and then on the.
Oh, perfect.
Yeah.
Oh, there's one here too, desk.
Check out those work.
Perfect. Thanks, though. So, your transformer model has a probability curve given like this, but you want to use a relatively high temperature to soften the curve to a more shallow curve. I don't know what the word for the shallow. So you can have a higher information gain and more entropy between your predictions. The reason you want to do that is to maximize knowledge transfer between the student model and the teacher model. So you have the two softmax layers, one for the student, one for the teacher, at the same temperature, and you calculate the loss between those two. But that is not enough because you also want to ensure that your student model is accurate and not just similar to the teacher model.
Is temperature, can I just consider it as a euphemism for standard deviation? And the way that it helps give a mission gain is just the fact that the standard deviation is wider, so I'm more likely to be, that I'm not as punished for being further from the mean.
Yep, I can explain it real quick. So temperature is a super common hyperparameter. This, I think it's a simple hyperparameter, no? Yeah, it's a super common hyperparameter used for tuning LLMs. So in this probability distribution, say for example, your sentence is he caked the dash. The most likely word here is probably ball. So when your temperature is low, your output is going to be ball with about a, say for example, a 95% probability. And then you have other alternatives like
Dog.
dog. I was thinking of it, but I didn't want to. I didn't want to. So you have dog and you have table. Okay. But those are not as likely, so you have 2.5% and 2.5%. So this gives you a more concrete answer. So it's good for actual users of LLMs, but the information here, you don't gain as much. You only have 3 predictions and only one of them has high confidence. So if you higher the temperature, you get more crazy LLM outputs with, unhinged answers and so on in real life. But in this case, it's useful because you have much more entropy. So here you have ball with maybe just 50%, and then you have kid with 10%. Oh, it was dog, my bad. And then you have table with also 10%, and then you have dog with 5%, and then you have a cat with also 5%, and so on. And you have a lot more options. So it might hallucinate, not hallucinate, it might be unhinged in real life, but you have a lot more information to gain. So you don't go all the way on temperature, but you want to keep it relatively high when you do knowledge distillation. So you have two main requirements. I should have put this in the slides, but yeah. You have two main requirements for the student model. One, you want it to be similar to the teacher because that's what you're learning from. And two, you want it to be similar to the real life Y values, which is the actual real answers in the training data set. Which is why your knowledge distillation loss is the combination of the distillation loss plus a hyperparameterized cross entropy loss between the student model and Y itself. So that is just like normal training, but parameterized, and this is the main loss, which is just between the student and the teacher.
So the distillation loss, is that computed by KL divergence, or how do you compare the two distributions?
That is one of the options, yes, but it just didn't specify here because as you know, after Hinton's paper, you have a lot more papers working on it who have created new losses which work better and better. And I didn't want to go into it at the moment, so I just left it at that. But that is the most popular one, you're right.
Okay.
Mhm. So everybody understand how knowledge distillation works? Any questions?
I missed the thing you were talking about with Japan. So it was actual loss.
He was talking about KL divergence. It's the most popular knowledge distillation loss. But I didn't go into it specifically here because there's a lot of them and I didn't really want to talk about it at the moment because I didn't know anything about it. Yep, that is just the basics of knowledge distillation. And I've explained in the slides that ZT and ZS are the logic layers, correct? And lambda is a hyperparameter to balance distillation loss and cross entropy loss. And T is the temperature to soften the probability curve. And more on knowledge distillation. One of the first experimental successes was Distil-BERT in 2018. It had 40% lesser parameters than BERT, 97% of the performance, which was a relatively small loss, and it was 71% faster. This was one of the papers I wanted to go into. I might consider going in a follow-up session, but I didn't read it myself, so I can't at the moment. But today it is much more widely used than that. So you know how popular models like Llama and BART and so on have different versions like 55 billion parameter, 30 billion, 7 billion. The smaller ones are always trained using knowledge distillation to an extent from the bigger ones. And you also add other strategies like quantization, not quantization, like pruning and so on to reduce the actual model size. Quantization is only used at the end for it's more like a last moment step to reduce the actual size, not the like you don't cut parts of the model out in quantization. You just reduce this. It's a compression technique basically. And any questions about knowledge distillation? That's the last slide. Perfect. So the next one is quantization. It is a very widely used technique and one of the most popular ones. It can be broadly classified into two types. First is post-training quantization, and the second is quantization-aware training. So the first one is a relatively crude method where a model is first trained and then the weights are converted to a lower precision. It's cheap, but not as efficient. So This is exactly what you think it is. You finish training. You can do this yourself too, actually. So if you see how people on Twitter post them running Llama on their MacBooks and so on, well, Llama is open source, so I guess they can. No, but that is also post-training quantization. Since a single person does not have the resources to retrain the model, it's usually converting the model to a lower precision after it's done end to end by the training company or research group or whatever. And the second is quantization aware training. So this is a more involved process where quantization is applied during pre-training or fine-tuning, and it requires additional computational resources because you are required to train again after applying it. It's much more efficient in the long run if you infer enough from it, but it's not cheap and regular people can't do it.
So the PF parameter.
Oh, yes, exactly. Mhm.
Q.
Yep. That is one of the papers I might consider going into actually. Question?
What do they mean by weights are converted to a lower precision?
So I can go into that slowly. So when you train your, so are you aware of data types? Like int, float, and so on
Yeah.
in basic programming? So those can be divided into much more types when you go at the lower level. So you have, at the highest, you have FP64, which is floating point 64 with 64 bytes.
Is it bits or bytes?
Bits, you're right, bits.
64 bytes.
See, it's bad. So you have 64 bits with the regular floating point distribution with the mantissa and the precision or whatever. I don't remember exactly how it goes. And then you have, this is not used that often because it's way too much information and no one really needs that often. FP32 is the most common for training. This is a 32-bit long floating point number. Go from 0 to 32 bits. And then you have FP16. This is used for some inference. So this is half the weight of FP32 without that much information loss. So it's commonly used for important inference mechanisms. And then you have FP8, which is pretty cheap. It's not that much information. If you use, you can never use this for training. You'll never reach the conversions you want because it doesn't hold enough information. But sometimes it's okay to use for inference if you're okay with making that trade-off of having lesser information and poor performance. So you have just 8 bits in one data type.
Isn't, I thought that, maybe it might be wrong, but I thought that you can still use FP8 for training where like basically like how like bits and bytes will like find it can be like the mean and median and then like you can set that to be like your 0 and then like with the FP8 value you can do like a map or like you can like compute values with respect to that mean and median for some value from some points. While for like outliers you will use FP16. So like what's the problem with like using that approach for like training?
You can definitely use
Okay.
that, you're right. But it's just not mainstream, and I don't know much about it either. You also have cases where you use FP8 for the weights and FP16 for the activations, because you usually have a lot more variance in the activations than the weights. The weights are much more complicated. So besides this, you also have int4, int8. Int8 is sometimes used for inference, but ints are never used for training at all, I think. And you also have some newer ones like BF16, which are custom made for machine learning. They're relatively new data types. And you also have TF32, 64, and so on. I think it stands for tensor floating point or something. This was made probably by NVIDIA recently, also for machine learning training.
What does BF stand for?
I forgot. I can check. You can check it.
Just to clarify, so you can apply this conversion to a lower precision to any of the data types? So for example, we can use not floating from integer, for example, in the order.
Oh, you mean when inference?
Yeah, conversion.
Yeah. You can use a lower data. All when you first finish training the model, it is traditionally in FP32. or FP64 in rare cases, but this causes the model to be very heavy, like large memory footprint. So if you go to FP16, it's half the size. You go to FP8, it's a quarter of the size and so on. So you can go as far or low as you want, but you will trade off performance and you will lose information basically. Question you asked first?
Yeah, so when you download the speed quantization, is it usually related to
That is FP8, correct. So again, if you're on the ML side of Twitter, you'll see some crazy people who post like, oh yeah, I ran this on my MacBook. Those are always 8-bit quant. Oh, recently Google released running an LLM locally in a computer. That is also, I think, 8-bit quantized because there's no way a 16-bit model is gonna, LLM is gonna fit in the computer.
They also do, I think, a lot of the spill and fill thing that you were talking
Yeah,
about,
uh-huh.
but at a much bigger scale and also with actual hard disk memory.
No way, that's
Llama.c, I know for a fact there's something kind of similar where the model itself is only loaded in certain components. So you will load a part of the model, then load the other part of the model, and then unload the rest in order to make sure that you have saving RAM.
That's crazy.
So, but that is obviously an extreme case on a very quantized model in order to make the thing infer on a consumer
Very
device.
small PC. That
Exactly.
is crazy though. Is it common in like edge devices usually?
Oh no, that was not an edge device. That was like a proper home computer.
No, I'm saying like for edge devices, is that level of quantization common?
I don't think no, I don't. I think even the inference it was at least it was running on a GPU, right? Trying to run 7 billion on an edge device that's not a GPU or like a accelerated device would be probably very slow.
7 billion would be 140 gigs times 9. That's like 20 gigs. Just in that. 20 gigs just for storage. That's crazy, yeah.
Inference if it's 48 gigs on a
Huh?
computer. It's 48
For
gigs.
inference, so I guess if you add KV and everything, it comes up to 48 gigs. Your laptop would probably run.
Yeah, that's how I checked it literally.
His laptop has 96 gigs of RAM. It's an MP max. So yeah, not a problem for him. Problem only for us. So did you check what BF was?
Yeah,
Brain floating one.
Brain floating point? Yeah, I see. I'm not sure much. I don't know much about that, but it's very commonly used for training for inference lately. This and this. And it's also common for companies making their accelerators to make their own data types as long as the model remains in-house because you can't open source it. Because when I was working at a company making our own accelerator, we made our own data type too. But that also causes its own problems where you can't test models out of Hugging Face because it is terribly inefficient. So you're forced to change all those and it's not cool. So people just stick with this.
So, my one thing I don't follow is, so I know the floating point is very commonly used, right? For things like tensor, like the tensor floating point or the brain floating point, what sort of things are they changing? Even if it's weak, that's fine, but what sort of things are they changing to the regular setup to make it better for it?
So they can change the precision, the recall, and so on using just this. It is an extremely powerful device. So within this 32 bits,
Right.
you know how floating points are stored. So it's not like you store 123.45 or whatever. So it has its own storing map there. You store the mantissa, the precision, the recall, and so on. You can adjust how many points after the decimal point you want,
Right.
how many before the decimal point. And some also allow you to express larger numbers by cutting off the last two precisions and giving you an exponent instead. So you can express much larger numbers at a lower precision and so on.
So is it the same way that like the IEEE standard is now like used all across computers, right?
Yeah.
The standard mantissa and floating point representation?
I think this is the IEEE ones, but these are invented just for machine learning by adjusting the precision to much more efficient values.
And these are basically on a case by case basis, right? There's no sweet spot that's been found for LLM as far as like what's the standard representation for 16 bits versus 32 or 64. Do you know what I'm saying?
Yeah, so BF16 is sort of a sweet spot. It's a generalized sweet spot for all of ML, but there, as far as I know, there isn't any for LLMs. But these are all, they're just like way older than even machine learning as a field. These were made in like the 80s and 90s or something. They're just used because they're common. But these two are ML specific. Yep, oh, my bad.
So to be very clear, quantization just means I reduce from 64 to 32 is 80. But how do we keep the information from losing too much?
Yep, so the answer is you don't like, you go down because you are ready to lose some information, but you also, there are techniques I will discuss soon in a couple of slides to minimize that information loss. And, yeah, I'll discuss it soon. Good question.
Yeah. Do you just cut it in half? So 64, then you cut it in half.
You don't truncate it, no. That's a good one again. So what you do is you usually have an average of all of them. So when it comes to weights, for example, they don't deviate too much. They all congregate towards a certain value. So I think you take about a value and then look at about an average of that, and they'll all congregate in that. So you lose much less information. Yeah.
Oh yeah, I was going to tell exactly that. I was so Alexei mentioned it earlier, but there is the bits and bytes, which is a awesome library that allows quantization without losing a lot of information. I think we got to about 4-bit quantization as well.
Yeah.
Yeah.
Floating points?
Yeah.
What do you even say?
Because if you like think like a mean and median of like actual data point, and like that's basically enough for them to like scale it up or down.
It's like everything is Gaussian, right? So they just bucket. It's all in buckets, and they also do subsets of tensors where each a subspace within a tensor is its own Gaussian, and that has its own again mean and deviation, and that is bucketed as well. So that goes a long way towards representing huge chunks without losing information. You mentioned earlier that it's also used differentially. So weights have FP16, activations have FP32. There are also similar layers like that that require high precision. Even with the bucketing, it doesn't help. And for those, they also use like a high precision for one layer, but then the majority of it uses lower precision, and you can get away with it.
That is one of the techniques I just mentioned it, but I didn't actually go over it because I didn't have time. But I might soon if I ever do a follow-up presentation.
Yeah, so Q Laura they use 4-bit quantization.
Yes, that is one of the case studies I really liked, and I might go into. For those who might still need one last explanation, I found a really good analogy online. So if you have a digital artist, they make their art piece in an extremely detailed fashion on their iPads or whatever, where they go small, fix every details. But when you see it on Twitter or the Instagram or so on, you see it in what 480p at most, which has sacrificed a lot of the details, but you get the gist of what you want to see. This is again the same. The trainers use super high precisions to make it powerful, but you don't actually need all that when you're actually inferring from it. Yep, and I have again included the data sheet for the H100 to show how the flops or the floating point operations change for it at different data types. So you can see at FP64, you can ignore the third column because that is not a single chip. That is a system of 2 chips. So the first two are what we want to look at. So for FP64, you get 34 teraflops, but if you go to FP32, you get 67, which is almost double. And then you go to TF32, which is NVIDIA's own data type, you get a much, much higher precision because it is custom made, much higher efficiency because it is custom made for machine learning and for NVIDIA GPUs. So for things like quantization, another very important thing is a compiler and a software library to go with it. So NVIDIA has their own in-house library called TensorRT, which is incredibly powerful. And one of the things I want to go into, but unfortunately, there's not a lot of information about it online because NVIDIA. So, you need these powerful libraries to ensure that you actually get the optimization you made the sacrifice for. Because if you're using, for example, an AMD GPU and you sacrifice from FP32 to FP16, you are not going to get 50% the size and 100% the performance improvement because it does not support it that way. You will have some loss over there. But when it comes to NVIDIA, you have almost a perfect trade-off. So you go to BF and you have BF16, that is an order of magnitude higher than FP32, which is just crazy. I don't even know how they do that. And FP8 and it goes to 4,000 and yep, Int8 is also 4,000 because it is not optimized for Int8 because Int8 is not used for inference. And after that, we can go into the four main post-training quantization techniques, some of which you guys have already brought up, which is really cool. So if you naively quantize post-training, it has historically shown poor results due to the high dynamic ranges of activation, which results in information loss. So what this means is that there's not a lot of variance when it comes to the weights, but when it comes to the activation values, there's always severe outliers. There's a high variance because there's just no general trend to it. So you have some severe outliers which are completely out of the range which you have chosen to quantize to. So those layers are completely unusable now, and it is almost as if you have cut that out of your model. So it could be a hit or miss. Maybe you don't need the layer, maybe you do. And if you do, that's a terrible loss to have. So naive is not the way to go. So you have four main solutions. The first one is mixed precision quantization. This is the one I mentioned earlier where you use uh, different data types for the activations and the weights. The most common one is the weights are FP8 and the activation are FP16, or the weights are FP16 and the activations are FP32. There's not much more to it, but I can refer to the paper soon. And after that, you have quantization at fine-grained granularity. I will explain that in a second. And then you have second order information for quantization. And the last one, you have outlier smoothing. So the last one is also an extremely simple mathematical operation where you apply a mathematical transformation to smoothen out the outliers to take a value lower within the range. I can go over the equation for that from the paper maybe next day because one, I'm not prepared, and two, we're out of time. Yep. Mm-hmm. So as far as I know, the outliers, there's no correlation between the outliers and the importance of the activation layer. So it could be a hit or miss. It could be that it's important, and if it is, you don't want to risk it, or it could be that it's useless. And in that case, you're gonna prune it anyway, so who cares, right? If it's gone, it's gone. So it's important that we still take it into consideration and not just let it go here. Question?
So what is the intuition of the second order information? Second order means second derivative, right? So what's the intuition of taking the second derivative?
So I will go over the paper and the equation for that soon, but what that technique actually does is it uses something called the Hassian distribution. I'm not sure what that means because I didn't read that much into detail into it, but it uses the Hassian distribution to find out the entropy in each of the activation layers, and it goes from there. But that is for later. I'm sorry, I cannot answer that. And at fine-grained granularity, let me think about it. I forgot. I don't. Oh yeah. Mm-hmm. Good point. Let me zoom in.
Okay, we did.
Say nothing here. Let me go down.
They check in the after the related work usually.
Methodology.
Yep. Is it here?
Content process. Yeah, that's just regular
It's
condensation.
just regular, yeah. Nothing new there.
In Hessian level quantization, mixed print assignments, higher Hessian spectrum are more sensitive to quantization and require high precision compared to small spectrum.
Mhm.
There exist 7 million parameters, each layer is a matrix of 10%.
I remember now that higher on the Hessian spectrum means that they have larger top eigenvalues, like the vectors for those specific activations.
So are they using SVD to test this?
I don't know. Apparently, it's because they're more sensitive to quantization and they require higher precision. So you identify the outliers and apply the higher data type, bigger data type just to those specific outliers. And the method to identify the outliers is using the size of the eigen.
How SVD works, would you grab the largest eigenvalues? That's what
I'm not sure. Maybe you're right.
No, yeah, yeah. For PCA, right? Like, usually use like if it's any image suppression. We usually have like the, I don't know.
Yeah, it's like the top of grades of that would be the most important ones, and
Yeah.
then you'd only take the top K.
So like the question that you'd save is that instead of having like an n by n, like you have a list of representation that's like n by like 20 by 20 by.
So this paper is actually really good for other optimizations. So it's called QBERT. They introduce a few, besides this, they introduce a few state-of-the-art methods for optimizations. But did you get anything from me? I didn't read.
I'm trying to understand the equation. The gradient of the first encoder is evaluated for a random vector. And then what? I'm not.
This is the G transfer.
Yeah.
My lady is not good with this.
Yeah, I'm good.
Nice. I'll probably go with the paper in detail and cover.
Well, I thought they just do like a product group afterward. So that makes sense. And then they drop your term for just a vector, which makes sense. You know, but then they just introduce an H1B just because they can.
But I mean, the high level is that they are finding top eigenvalues, right?
So they're trying to basically if I'm going to define, they're trying to diagonalize like the actual gradient, which is like the H1B, right? So that's how I'm interpreting it. And in order to do that, they take a gradient and they just drop one of the product, and that's the part I'm on. Right, because like they have a product where they just drop the second term.
Oh, because B is independent to W1.
Oh,
that
okay, yeah, okay, that makes sense. So, like, why is it independent from? Where do you say that?
B is,
Oh, okay.
yeah, random vector, so it's
So they take a gradient, they drop it, and then they diagonalize it. In this case, like, we have AB equals to,
which creates the Hessian matrix.
so is usually like the AB equals to It's like that, so maybe matrix and that.
I guess if I want to just look at the high level of it, they are obtaining Hessian matrix out of the gradient set, right?
Yeah.
So the important thing is they need the Hessian matrix in order to perform quantization that's Hessian aware,
Mhm.
because they are
What
computing
is that shit?
the Hessian
What's
distribution.
the, what's the mean for it?
The top eigenvalues are more sensitive to quantization.
So it's
Right.
easy to identify the outliers using
Yeah.
this.
So they gain the Hessian, identify outliers, and they're able to quantize to that. That makes sense.
Yeah.
But I'm not sure how they got, like, I don't intuitively understand it. I just get it from the
Maybe
surface.
actually you can always find out again about it, so.
Oh.
Like, at least the part of those stuff from linear, we need an inverted. Is that saying always invertible?
I don't know.
Huh?
I think, Hessian matrix still, if I remember correctly, it's like, it's just some function and it's a square matrix with the second order partial derivatives of whatever function that you're passing in. So what essentially it's trying to do is like, it's trying to map or try to understand how the function's curvature is. If we give it some data, and any data has some curvature, so the Hessian matrix just identifies, like in each, like in some higher dimension, in this dimension, this is what the curvature of the data looks like. So once it knows that, I think that way it like increases how it can like do the quantization, because it understands how it's shaped, so it can like.
You basically pull like the most important eigenvalue.
Yeah. Okay. So it's like, it's basically saying that like, if I give you something unstructured and you can identify, well, these are the 5 things that are most important to making this thing.
Yeah.
Then you can put the five
Basically
together.
approximated.
Yeah, in some way. Because all the Hessian matrix is doing is like telling you, well, this is the shape of the distribution as mapped by the like second order derivatives, because that gives you the idea of the curvature of the function.
I think this is a stupid, I'm gonna ask a stupid question. How do you know to take the second derivative?
It's how you know where the function curves. If it's
Oh, right.
that's how you know
Right.
inflection points, right?
Yes, okay, I forgot.
Or you can also use secondary to get the outliers because you have the more significant.
Or high values, basically.
Yeah, the high values, the most,
High values.
what you call it, the parameters, significant parameters.
Right.
Yeah. Kind of makes sense, but I'm gonna have to go more into it.
How the W1 is like 5 against W1.
W one at the week. So I think.
Yeah, so why are we taking it with respect to the weight matrices in general?
Because we're basically, I think it's the back proposition, where you're finding gradients with respect to your weight. And you do
No,
that.
but because it says that it has to be fixed for the first encoder.
Oh, wait, is it true? So
Yeah,
I think
after the equation, it says for the first encoder.
right, so I think there's expected like a transformer.
You're right. I'm using like trying to like, rating for the encoder, like, that's G.
Yeah.
No, but W are the weights.
Did they specify where W sub one is?
Yeah, exactly, that's right.
I don't see W sub one in.
Go down a little.
Maybe, I think it's.
Should be above.
Yeah, maybe the.
It's not gonna be here. This is like the different sections. It'll be within mixed precision.
They just fastly drop the weight. Yeah, I guess.
Classic.
It's just
I think it's just the weights.
If you want to, I mean, at least at a high level, though, are we clear on what it's doing? I think the idea is that we just evaluate the Hessian matrix, and somehow they are able to obtain the Hessian matrix through that series of equations.
I'm not understanding how they can get this matrix from that.
Oh no, that part I don't follow.
I don't.
No, because I saw it somewhere, it's just like you take a function, right? Like you pass in some function and then you do the matrix by taking. After, you know, it's written like, it's in the-
Oh.
Yeah, it's just the.
Khan Academy, damn stupid. If
If
the answer is on Khan Academy, it's on you, bro. You're just not good enough. Damn.
Well, click on it, I'll volunteer, I'm like.
No, I'm not good enough. I had to look it up.
Yeah, that's. You pass the function and it's like, okay,
Oh, I see, okay.
Well, but how does that relate to?
The gradients, whatever they're taking.
I only remember the intuition, I don't know the.
It's just a matrix of second derivatives.
Yeah.
Okay, well,
It's
how would
good
you?
for knowing how local, like if you give it for some function, it's good for knowing, like locally, this is how it looks. Like around some points that you define, like it evaluate at some point, like near those points, how it looks is what it's basically trying.
Right. Well, so question is how do we obtain the Hessian from the model?
Exactly my question, that's what I was like, that's what I'm not following, like I know if you pass a function, like you can have some variables that are in the function, you can.
Maybe you just take the second derivatives.
Yeah, but like,
Of what?
in the paper, why are
weight
you
against-
taking it with respect to W1?
Usually we backpropagate, when you backpropagating, it's against loss, right? But you
Yeah,
don't
yeah.
have a scalar.
Like, why is there what's W1?
Yeah. I mean, if you want, we can table this for later discussion or
Mhm.
talk about it on Discord, but
Sure.
yeah, that's something that's,
Can you send the link to the paper?
yeah.
Mhm. I'll send the link. And there's a few more which I referred to, but I didn't discuss
Yeah.
in detail. I'll send to. Mhm.
If you could figure it.
Mhm. Is Mikhail next week or no?
Yeah, but
We can push it.
yeah.
I can go after this. I'll just go over a quick what's left.
Awesome.
Yeah, I don't have much more actual slides, but yeah. So after these four, I have quantization of weight training, which just involves fine tuning after the process of quantization. I can discuss the training methodology for that. It's really short. And then we have pruning. You have two types of pruning, which is structured and unstructured pruning. I can discuss how to prune efficiently, which is also there's not much to it. It's a pretty done and dusted technique, which is still very useful, but there's not much new in it. And then you have sparsity. This is very interesting because I learned some new things I actually didn't know before, like how bigger but sparser matrices are more efficient and faster than more dense matrices of the same size. So when it comes to models, you prefer, when it comes to transformers, you prefer sparser models than more dense ones because they're when you want efficiency, not when you want performance. But you don't lose much performance apparently. So I want to discuss that. There's a few kinds of papers where they discuss transformers which are sparse. And then mixture of experts. This is again training methodology where you have multiple models and go from there. And then you have architectural optimizations. This is just a really nice chart I found, which goes, this is from 2021, I think. But for that time, this is the best coverage of all the different patterns when it came to training transformers. We can discuss some of them from there. So that is memory optimized once, low rank once, and so on.
This might be a stupid question, what's the difference between pruning and dropout?
Uh, so pruning, you do it after you finish training the model. Like you have a model which works. Hmm?
It's only during inference, like after you train the model, that's when you like drop some nodes.
No. Pruning, you do it like before inference and after training. Like given a model that works and which is kind of big, you prune it to make it smaller. Dropout layers is a training technique where you drop the layers as you train. Pruning is not a training technique.
Yeah, so pruning, you're just pruning like the decision tree, not pruning like the layers or like the nodes.
Like the decision tree, but you're pruning the neural network, yes.
Yeah.
But
So
it is
you're-
like pruning a
you're
decision
basically
tree.
pruning the connections between the layers.
Yep. You're dropping layers completely, but like after training.
A lot of times some layers have dead neurons where the activations are always zero because the value is super low and like exactly. So that was a very obvious thing to drop out, but then there are also more aggressive techniques that actually cause drops in performances. But
Like, is it, you're talking about pruning?
pruning, yeah. So you just completely use those weights, and then in inference it's faster at the cost of at the cost of that, or like at the cost of accuracy.
So my question is like, if I have like a layer that goes from like 4 to 2, it should have like 2 raised to 4 fully connected layers.
Right.
So after pruning, like I understand like some of the weights are not necessary, some of the connections are necessary, so I have only have like 3 connections.
Yeah,
And that's pruning.
Does pruning remove like whole layers or connections?
connections within.
Yeah, that's what I
Oh.
was.
It also
Like,
remove
it
layers.
doesn't say like this.
Wait,
layer
wait,
is shared.
It also removes layers.
It does?
Oh, it does?
That's what I thought.
I
could be wrong.
I thought,
You may-
That's what, that is exactly what my question was like.
Oh, okay, yeah, see.
I think
I'm not sure.
layers would be too excessive, right? Because the idea is that it's chain rule we use for training, right?
Mhm.
So each
But
layer,
if you merge the layers. then-
each layer feeds into itself, exactly. So you can remove the layers that have high value, not the layers, the neurons that have high, that have low weights, exactly, low activations or no activations, because that influences the final chain a lot further, almost like the domino effect. You're minimizing the impact of the domino effect by only saying maybe 5 or 10 neurons are not useful in the final
Okay, I
thing, and they
see.
don't influence the decision as much,
Maybe, I don't know, I think you're right.
right?
Layer pruning would be actually finished.
You know, I don't want to do by saying
Yeah.
convolution.
Okay, there's actually a layer pruning.
There is.
The technique used to reduce latency and computation costs of a transformer model by removing redundant layers or heads from a thing.
Oh, wait, heads make sense. You could remove heads.
Yeah.
Yeah.
How do they add, how do they create MHA though? Like, how do they create?
Like, how do you decide which one to remove?
Well, because if you have multiple heads.
What if you,
having different
what if you
things, right?
merge
So-
layers?
You could technically merge.
So you find like the one that you're like maybe.
You could technically merge layers.
Oh, there's types of.
Oh,
If they're redundant layers, you can merge them.
What's a redundant?
how would that work?
They don't change the, during power propagation, they don't change the.
Oh, they
value
switch it out, okay.
Yeah,
fair.
so you have,
You could just merge the layers.
you just merge layers. together.
No, but the thing with MHA is that we need to have the same output, right? After attention, you need the same output vector.
Well,
If you're
well,
removing
yeah.
a head, you can't.
Right, but you just like double that.
Junaid, what if you take into consideration quantization at the same time? If you quantize and basically truncate some of the information, maybe there is no information change at all, in which case it's not gonna change.
Oh,
It's
well,
just not gonna change.
I was confused about the architecture part for transformers,
Oh.
because the dimensionality of the output tensor has to be the
It's
same.
not still be the same, yeah, but
As the
for
input.
instance, say you
Maybe
like-
you can.
You can like convert their, one of the calculations to that head.
And then just double up
pick
on-
one.
Maybe, yeah, that might be something.
But then like, it might mess up.
But
your
that's-
act- It might,
wait.
it might mess you up because you'll get more weight
Yeah.
for like that specific head then.
You looking at
Like half the head in that point.
Yeah.
I think we probably need to read some actual
Yeah.
literature.
I will cover the next presentation that too.
Alright, cool.
And after this, there were a few more, like, this is my last slide, but there were a few more transformers which were custom made for things like this, which I really liked. I'll go over them too. And how do I stop my recording now?
Awesome, thank you.
Yeah.
Thank you guys for coming.